In chapter 5, we looked at the stereoisomerism. We learned about chiral center, and we know that the chiral carbon is a carbon that has 4 different groups bonded to it. We learned about the difference between enantiomers and diastereomers. Enantiomers are mirror image of one another, but diastereomers are not. In this video, we want to learn how presence of a chiral center can influence the chirality of the whole molecule. If we have a compound with a single chirality center, that molecule is always chiral. So one chirality center, the molecule is chiral. That's it. However, if we have a molecule that has more than one chirality center, that is not always true. There are going to be cases that molecule with 2 chirality centers is not chiral. So if you look at 2 examples here, we have trans and cis isomers here. Both of them have 2 stereogenic centers or chiral centers. This carbon is attached to the methyl, attached to the carbon that has 2 hydrogens, attached to the hydrogen, and a carbon that has methyl. So 4 different groups, it is chiral carbon. Also this one, and it is the case in these 2 as well. Now what we see is that the trans isomer is actually chiral, but the cis isomer is not, though it has 2 chirality centers. So why is this? What's happening here? If you look at the molecule, the cis isomer here, if a molecule has a plane of symmetry, so the cis isomer has a plane of symmetry. Imagine there is a plane that can pass through the middle of the molecule, meaning that one part of the molecule is exact the same as the other part of the molecule. We call that isomer a mesoisomer, and the mesoisomer is not chiral. It is a chiral molecule. So in details, if you want to know what is the scientific reasoning behind it, when you have meso compounds, one part of the molecule, one carbon, one stereogenic carbon, gets the R configuration or S configuration, but the other part gets the opposite configuration. So meaning that, imagine if it is R, the other part should be S. And we know that R and S configuration, they rotate the plane polarized light in 2 different directions. One of them is positive, the other one is negative. Now in meso compound, because we have plane of symmetry, meaning that one part of the molecule is exact the same as the other one, so these 2 chiral centers basically rotate the plane polarized light in 2 different directions, but into same extent. So basically they can cancel out one another. And what you see when you put this molecule in the polarimeter, you just see the straight light coming out of it. You don't see any rotation because they will cancel out one another. So that's the reason the mesoisomer is not chiral. It is always a chiral molecule. So we just learned that the compound with chirality centers can be achiral because of the plane of symmetry, and we call that compound a meso compound. Meso compounds are superimposable to their mirror images. So if you imagine there is a molecule right here, we have 2 chirality centers in this molecule, 1 and 2. Now if you look at this molecule, one half of the molecule is exact the same of the other half, meaning that there is a plane of symmetry that is passing through the molecule. So this compound is a meso compound. Now if I imagine there is a mirror and I draw its mirror image right here, that would be the molecule. So these 2 structures are mirror image of one another. Now, a meso compound can be superimposable to its mirror image. So here is the compound in the left. These chlorines, they are coming out of the plane of the page. Two methyl groups right here. I didn't attach the hydrogen, so it's easier to follow. And there is a hydrogen in the back. And this structure right here, it's the mirror image of the molecule in the left. Now, if I try to fit them on top of each other, so I can simply do that. See? So the chlorines are matching, hydrogens are matching, methyl groups are matching. If you even attach the hydrogens on methyls, they would match as well. So what does this tell us? That means these two compounds are identical. They are the same compounds because they are superimposable on top of each other, meaning that a meso compound cannot have an enantiomer. You cannot draw a mirror image for that. Its mirror image would be the same molecule. So have this in mind and make a note of that. Meso compounds don't have enantiomers. You cannot draw enantiomers for a meso compound. A practice problem here, so we are supposed to draw stereoisomers, all stereoisomers for this molecule. The first step is to identify all the chirality centers. So by looking at this structure, I can find two chirality centers in this molecule. And then if you remember, we had a formula 2 to the power of n. N was the number of chirality centers. So 2 to the power of 2 gives me 4, meaning that I can draw 4 stereoisomers for this molecule. Now to draw the first stereoisomer, what you can do, you can either draw both of these bonds in wedge, or both of them in dash, or one in wedge and the other one in dash. It depends on you. I would like to make one of them in wedge and the other one in dash. So the top one, I make it in wedge, and the other one, the bottom one, I make it in dash. Now, so this is the first stereoisomer. To draw the next one, what you can do, you can draw the enantiomer for this molecule. And to draw the enantiomer, we need to flip all the configuration. So the top OH was in wedge, now it should be in dash. And the bottom one must be in wedge. So two stereoisomers till now, and they are enantiomers. To draw the next stereoisomer, what you can do, you can draw the diasteromer for this molecule now. And to draw its diasteromer, we need to keep at least one stereogenic center the same. So I would like to keep the top one the same and change the bottom. Or I can keep the bottom the same and change the top one. Okay? So there are 4 stereoisomers drawn on a board here. Therefore, you may think that the question is answered. However, you need to be very careful here. What is happening here is a meso trap. So if you look at these two structures, they are basically mirror image of one another. However, if you look at this molecule, one half of the molecule is exact similar to the other half, meaning that there is a plane of symmetry that is passing through this molecule. Therefore, this compound is a meso compound. And if you remember, we cannot draw a mirror image for a meso compound. These two molecules are identical. So be very careful. When you have a meso compound, you would have one stereoisomer less than what you predicted. Therefore, this molecule has 3 stereoisomers overall. Let's talk about Fischer projection. So Fischer projection can also be used to represent molecules with chirality centers. And most of the time it is used when you are dealing with a compound that has multiple chirality centers. So this is the Fischer projection, an example of Fischer projection where we have 3 chirality centers. In the Fischer projection, each intersection is a chirality center. So there is a carbon here that is connected to 4 different groups. So it's a chirality center. So let's make a note of that. So in this structure, I have 3 chirality centers, 1, 2, and 3. I didn't draw this carbon as a like intersection because it has 2 hydrogens attached to it, so it's not a chirality center. Also, the carbonyl carbon, it is connected to oxygen with the double bond, so it cannot be a chirality center. When we look at Fischer projections, any groups that is drawn in the horizontal line, it's coming out of the plane of the page, and we show that with the wedge bond right here. And anything that is drawn in the vertical line, it's going into the plane of the page. It is shown with the dash bond. So I made the model of this molecule. Let's look at it together. So this is the model that we have. This is the carbon at the intersection. It is a chiral carbon because it is attached to 4 different groups. This is 1 hydrogen, OH, methyl, and ethyl, which is CH2, CH3. Now these 2 groups, they are coming out of the plane of the page. So hopefully it is clear that they are coming out of the plane of the page. We show them in the horizontal line. And these 2 groups, methyl and ethyl, they are going into the plane of the page, and we show them in the vertical line. So this is one way that you can draw a specific molecule using Fischer projection, especially when you have multiple chirality center. However, you can even look at the molecule in this way and draw its bond line structure. We can even look at the molecule in this way and draw its Newman projection. So I didn't change anything about these molecules, right? They are just different ways of representing the molecule. We want to see how can we look at the Fischer projection and convert them to bond line structure with the right stereochemistry. There are a few steps that you need to follow here. You can even make a molecule with your model kit and rotate it in a space and draw it as you can see it. However, if you don't have your model kit, you need to follow these steps. So step number 1 is to number carbons. Find the longest carbon chain and number it. So in this structure, this is carbon number 1. Each junction shows a carbon 2, 3, 4, and 5. The next step is to draw a bond line structure that matches the number of carbons. 1, 4, and 5. The third step is to determine RNS configuration for all the stereo centers. So this carbon is a chirality center. It has 4 different groups attached to it. This carbon is also a chirality center. And I'm going to determine RNS for both of these. So I start with carbon 2. Oxygen is number 1. Hydrogen is my lowest priority, gets number 4. Then between methyl group and this carbon chain wins. So it is number 2 and methyl is number 3. Now let's count. We have 1, 2, 3. So I am rotating counterclockwise, which means I have S configuration here. However, hydrogen, which is my lowest priority, is in a horizontal line, meaning that it is pointing towards me. Therefore, I need to flip the configuration. So this is R. For carbon 3, chlorine is number 1. Hydrogen is number 4. Now between ethyl group and this carbon chain wins. So this is number 2, number 3. Now let's count 1, 2, 3. So again, I am rotating counterclockwise. This should be S. However, the lowest priority is pointing towards me. I need to flip the configuration. This one is R. So then what you can do is to randomly put the groups on the chiral centers in a bond line structure and determine the configuration. If the configuration matches, you get the right structure. If not, you need to switch the groups. So let's start with carbon 2. So on a carbon 2, I have a hydrogen and OH to put. This is carbon 2. This is the methyl. And this is the carbon chain. So I need to put hydrogen and OH. Let's put OH in wedge and hydrogen in dash. Okay. Then I need to determine RNS configuration for this center. Oxygen is number 1. Hydrogen is 4. Carbon chain is number 2 and methyl is number 3. So let's count. Have 1, 2, 3. So I am rotating clockwise and the lowest priority is in the back. So the configuration here is R, which matches the configuration that we figured out in the Fischer projection. Now for carbon 3, I need to do the same thing. So to carbon 3, we have chlorine and hydrogen attached. I'm gonna put the hydrogen in wedge and chlorine in dash. So now let's figure out the configuration here. Chlorine is number 1. Hydrogen is 4. Ethyl is number 3. And carbon chain is 2. Now let's count. So it is 1, 2, 3. I am rotating clockwise. However, the lowest priority is pointing towards me. Therefore, I need to switch that, which gives me the S configuration for this center. However, if I compare this to the Fischer projection, they don't match. In this situation, what I can do, I can just switch these two groups. So I'm gonna put the hydrogen in dash and chlorine in wedge. Now let's count. 1, 2, 3. So I am rotating clockwise and the lowest priority is in the back. So the configuration on this carbon is R. which matches this configuration. So these two structures are identical. And this is how you can convert the Fischer projection to bond line structure. Now, how can we convert bond line structure to Fischer projection? So the first step again is to number all the carbons. So I'm going to start numbering my carbons. And then identify the chirality center and determine RNS configuration. So this carbon right here is the stereogenic center. This carbon right here is the stereogenic center. They both have 4 different groups attached to them. Now let's determine RNS configuration here. So I'm going to start with carbon 3. Oxygen is number 1. And let me draw the hydrogen as well. Also for this one. Okay. So oxygen is number 1, hydrogen is number 4. Then between the isopropyl group and this carbon chain wins. So this is number 2. And then we have number 3 here. So let's count. So it's 1, 2, 3. I am rotating clockwise and the lowest priority is in the back. So the configuration here is R. Now let's look at carbon 4. Carbon 4, chlorine is number 1, hydrogen is 4. Now between this carbon chain and the ethyl group, carbon chain wins. And then we have number 3 here. Now let's count. So 1, 2, 3. I am rotating clockwise. Hydrogen, the lowest priority is in the back. So this configuration is also R. Okay. Then the next step is to sketch the Fischer projection. So the rule here is the number of horizontal lines that you draw should match the number of chirality center that you have. So I have 2 chirality centers here and I'm going to draw 2 horizontal lines. Then I have 1 vertical line that is passing through them. So let's number the carbons here. This junction shows carbon 3. This is my first chirality center. And then this is carbon number 4. Now to carbon number 3, I have carbon 2 attached, which has 2 methyl group attached. So this is carbon number 2 with 2 methyl groups. And to carbon number 4, I have ethyl group attached. So I can draw it as CH2, CH3. So this is carbon number 5 and 6. Now, again, similar to the conversion of Fischer projection to bond line structure, we can randomly put the groups on each chirality center and figure out the configuration. If they have the same configuration, the structure is correct. If not, we need to switch the groups. So let's start with carbon 3. To carbon 3, I have OH and hydrogen attached. So I'm gonna put OH here and hydrogen here. So you can randomly just do it. Now let's figure out the configuration. Oxygen is number 1, hydrogen is 4, this group is 2, and isopropyl is 3. So let's count. This is 1, 2, 3. I am rotating counterclockwise, and my lowest priority hydrogen is in the horizontal line, so I need to flip the configuration. Therefore, this is R, which matches the configuration that I figured out in the bond line structure. Now for carbon number 4, I have chlorine and hydrogen attached. Let's put chlorine here. And hydrogen here, so you can just randomly do it. And now let's figure out the configuration. This is 1, 4, this is 2, the carbon chain, and ethyl is number 3. So now let's count. This is 1, 2, 3. I am rotating counterclockwise, and hydrogen is in the horizontal line, so I need to flip the configuration. So since I'm rotating counterclockwise, it is S. I need to flip it. This is R. Alright, so now both of these have the same configuration on carbon 3 and carbon 4, so these two structure matches. Previously, we talked about cis and trans isomers, so we can use cis and trans terminology when we have similar groups attached on each carbon of alkene. If those groups are in the same side, we have cis isomer, and if they are in the opposite side, we have trans isomer. Now, sometimes across the double bond, we have 4 different groups attached. In this situation, we use E and Z notation instead of cis and trans notation. Now, how can we use them? How can we assign E and Z to a double bond with 4 different groups attached to? So the first step is to prioritize the groups attached to the carbon-carbon double bond based on the atomic number. So let's look at this structure. This carbon right here, it has 2 groups attached to. So between these 2 groups, nitrogen gets number 1 and hydrogen gets number 2. Nitrogen is the priority here. And then I need to look at the second carbon. There are 2 groups attached to it. Fluorine gets number 1 and ethyl group gets number 2. So now that we have top priorities on the same side, we have Z isomer. However, if I redraw this structure, okay, so again on this carbon, nitrogen gets number 1, hydrogen is number 2, and on the second carbon, fluorine is number 1, ethyl is number 2. Now the top priorities are on opposite sides. So I have E isomer here. This is how we assign E and Z to the double bond with 4 different groups attached to.